बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश्रह ली सदरी वयस्सिर ली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Today we will do section 2.2.1 Birefringent Materials from the book Quantum Mechanics by Beck. There are certain materials called birefringent materials which are extremely useful in modifying the polarization of a wave. Before getting into details, we'll start with a brief review of wave propagation in media. A medium such as glass or water has an index of refraction n associated with it. The index of refraction is determined by the speed of light in the medium V and is given by n is equal to C over V. Inside the medium of index of refraction, n becomes k is equal to wave vector, omega is equal to angular frequency, c is equal to speed of light, f is equal to frequency, lambda is equal to wavelength, v is equal to velocity of light in a medium, n is equal to refractive index. The wave vector k is equal to omega over v. The refractive index n is equal to speed of light in vacuum over speed of light in medium. From this we find that the speed of light in medium is equal to speed of light in vacuum divided by n. K is equal to omega over v. If we substitute the value of v, which is the speed of light in medium, we get k is equal to omega n over c. We know that omega is equal to 2 pi f. If we substitute that also in the wave vector k, we get k is equal to 2 pi n f over c. We know that c is equal to f lambda. From that we can find lambda is equal to c over f. If we substitute this in the wave vector, we get k is equal to 2 pi n over lambda. We know that k is equal to n2 pi over lambda. The phase shift between 2 points in a wave separated by distance z is phi is equal to kz is equal to n2 pi z over lambda. The phase shift depends on the index of refraction. For normal materials such as glass, the index of refraction depends on the frequency, wavelength of the wave, a property known as dispersion, but not on the polarization or direction of propagation. Such a material is said to be isotropic. A cubic crystal is an example of isotropic or isometric material. In this case, the sides of the cube are of equal length. A1 is equal to A2 is equal to A3, and A1 is perpendicular to A2 and A2 is perpendicular to A3. That makes 90-degree angle with respect to each other. They have same optical properties, that is refractive index in all directions. Birefringent materials are anisotropic. The index of refraction depends on the polarization. Such materials are crystalline in structure, having one or more preferred direction in space. In uniaxial crystals, light polarized along a particular axis called optic axis has one index of refraction, while light polarized perpendicular to the optic axis has a different index. In biaxial crystal, there are three indices of refractions associated with polarization in three different directions. What causes this difference in the indices of refraction for different polarization? Remember that crystalline structure have a very specific and ordered arrangement of atoms in a material. Imagine, for example, that atoms are arranged in sheets and the sheets are stacked on top of each other. It's not difficult to imagine that the field polarized parallel or perpendicular to the sheet will behave differently in such a crystal. We can always decompose the polarization of a wave into two orthogonal components. Because birefringent materials have preferred direction in space, it is natural to choose components associated with these directions. The direction associated with the lower index of refraction is referred to as the fast axis because light polarized along that axis propagates at faster speed. Conversely, the orthogonal direction is referred to as the slow axis. Light polarized in this direction propagates at a slower speed. I would like to discuss with you the uniaxial crystals and biaxial crystals in a little more detail. The uniaxial crystal is an optical element that has single optical axis. When a light beam passes through a uniaxial crystal, the light beam splits into two rays named as the ordinary ray O ray and the extraordinary ray E ray. In a uniaxial crystal, one of the refracted ray obeys the law of refraction and is therefore called the ordinary ray, whereas the other ray does not. It does not lie in the plane of incidence and is called the extraordinary ray. One example of uniaxial crystal is in a hexagonal crystal. In this case, A1 is equal to A2 is equal to A3 and it is not equal to C, and C is perpendicular to A1, A2 and A3, and the angle between the axes is 60 degrees. Another example of uniaxial crystal is rhombohedral, lattice or trigonal. In this case, A is equal to B is equal to C. The sides are equal, but alpha, beta and gamma, the angles are not 90 degree. An example of this is the calcite crystal. Another example of uniaxial crystal is tetragonal crystal. In this case, side A is equal to side B, but it is not equal to side C. Alpha, beta, gamma, the angles are equal to 90 degree. This figure represents unpolarized light passing through birefringent crystal. We get two rays, ordinary ray and extraordinary ray. The ordinary ray obeys the Snell's law, whereas extraordinary ray does not obey the Snell's law. The extraordinary ray can be faster or slower than the ordinary ray. An example of uniaxial crystal is calcite. The refractive index across ordinary axis is 1.658. The refractive index across extraordinary axis is 1.486 and it is a trigonal crystal. Another example of uniaxial crystal is quartz. Refractive index across ordinary axis is 1.54425. Refractive index across extraordinary axis is 1.5538. It has a hexagonal structure. A biaxial crystal is an optical element that has two optic axes. When a light beam passes through a biaxial crystal, the light beam splits into two rays. Both are extraordinary rays. All the monoclinic, triclinic and orthorhombic crystal systems are biaxial crystals. An example of biaxial crystal is orthorhombic. The sides A is not equal to B and it is not equal to C. Alpha, beta, gamma, the three angles are 90 degree. Another example of biaxial crystals are triclinic. In this case, A is not equal to B and it is not equal to C. The sides are not equal, and alpha is not equal to beta and it is not equal to gamma. The angles are not equal. The third example of biaxial crystals are monoclinic crystals. The sides A, B and C are not equal. The angle alpha and beta is equal to 90 degree, whereas the angle gamma is not equal to 90 degree. In the end, I would like to summarize the definitions of birefringence. When a beam of non-polarized light passes into a calcite or quartz crystal, the light is decomposed into two beams that refract at different angles. This phenomena is called birefringence or double refraction. Snell's law holds for the ordinary ray. May Allah bless us all. Thank you for watching. Allah Hafiz.